This is where it's going to get a bit interesting here. We'll coming back to this in just a second, but if we look at figure, this is figure one. I'm pretty sure that was no dihedral, and they ended up putting in a dihedral here, but a little bit more. So we're talking about airplanes. Airplanes not only have a dihedral angle, but they also have a sweep back angle. And it turns out that what they've done with figure two is not only do they have this dihedral in here, they have sweep back. The shoulder actually points backwards. And I had a chance to talk with the chief designer about that when I saw it. And I said, "You guys did this to avoid the singularity, right?" He said, "Yeah." And that's also clever because a lot of times it might be that sweep back almost gets you all the help that you need because a lot of it is like straight out is what you're worried about. How often do you really put your arms back like that? So that means that's like it's a position you just wouldn't get to. That's why they were able to put the ketchup up so easy. They were able to go through. You say, "Oh, looks like they passed through that singularity." It's like, no, they did because the singularity is pointing back. And that's why I was like extremely disappointed when the Gen 2 a digit came out, and this is what the shoulder looks like now. It's an FAR design. So Apollo is the only example s- of a company trying to do shoulder without any rotary drives at all. Okay. And we're going to kind of break down how they are doing that right now. But pretty much it looks like the flexion goes right along this red axis here for sure. And at this point here is where the abduction happens. And it looks like the rotation also happens up there. And the other thing we might notice is that the rotational axis here is offset from the center. So this is no longer concentric. And the question is, why are they doing that? Okay, so all right, Mara. So are you ready for today's presentation?
I'm ready. I'm looking forward to it, Scott.
Okay, so I have to ask you, are you ready for the cold shoulder?
I need to have a cold shoulder.
Yeah.
I
Well, basically, it's the question is, why are novel shoulder designs being ignored? And so, just as kind of a little bit of a refresher, the past couple of weeks, been looking at different parts of the humanoid kinematics and trying to classify them and understand them and look at the design space. And we began with the hips and, figure out how to classify them and get an idea of what kind of designs are out there. Are there any improvements or evolutions in those designs? And of course, before we get started, we had to describe or get a couple of ground rules as far as the description of the motion that you have in the hip. And these are typically called, flexion, abduction, and rotation. We use that, FAR is kind of a shorthand notation of what these different actuators are trying to be doing in the humanoid bot. And with a reminder that, of course, the humanoid hip is actually a ball and socket joint. And because it's a ball and socket joint, you have 3 degrees of freedom, which allow you to get the red flexion and then, the green abduction and also the blue rotation right around the center of that. And so as a result, humanoid bot companies have tried to emulate that. They can't do it with a ball and socket for reasons. Okay, we'll get into that later. So what they do is they use pretty much a serial stack of actuators that are able to that are usually perpendicular to each other that'll give you the oops, sorry about that, give you flexion, abduction, and rotation. And you can organize these letters any way that you want. So your first actuator up here does not necessarily have to be flexion. And as a result, you can look at different kinds of possible designs that would be out there just by organizing them differently. And what we've done, of course, is that we kind of looked at the overall design space and said that, well, about half of it's been explored for the hip. And, at first it looks like, this is the dominant one, but the consensus shifted that after the first generation, everyone dropped this except for Optimus. And they pretty much moved over to here. So the consensus for the hip seems to be using the FAR kind of hip, and with a couple other outliers that are out there. But for the most part, everyone's kind of moving that way. So the question is, what's going on with the shoulder? Is it kind of the same thing? Because if we look at the waist, and when we looked at that, we saw that it has a much broader design space and it's much more populated. And there's absolutely like no consensus in that design space of which is the preferred way of doing it. Even within the same companies, they will have maybe 2 hips, like Unitree has 2 different bots and different hip designs. So um, So what we have is the question is what's it going to be like for the shoulder? And so the first thing we want to do is again define what the shoulder movements look like. And lo and behold, they use the same terminologies they use for hip. We've got flexion, extension, or just flexion. We have ab and adduction, uh, and then we also have the rotation of the shoulder. So we have those three. And again, we shouldn't be surprised that the shoulder joint is sort of similar to the hip joint, not exactly the same, but very similar. It's a ball and socket joint, and all the rotations are pretty much done around the same location. Okay, and there's a little bit more that kind of goes on there with the scapula, but we'll kind of get into that a little bit later. But for the most part, that's where your rotations happen. Okay, so we should not be surprised that when some of the first humanoid bots came out, that they ended up having an arrangement like this, which turns out to be an FAR arrangement. So you have this actuator here, which is horizontal, which rotates over on the red axis, which is your flexion. And then it's carrying a motor which is sort of perpendicular to the other one, sticking out of the screen in a sense. And that's this green actuation that happens right there on that pivot point. And then that in turn is carrying another motor, which is now parallel to the upper arm direction, which is able to then rotate to give you the rotation along the arm. So that's how you get you 3 degrees of freedom in there. And sort of a better view of this might be the next generation of Optimus, where that was the Bumblebee. And then is that you can sort of see how the actuators are exposed here and get a better idea of how the actuators actually form the joints and how they're kind of stacked together in different ways to be able to get that rotation. And if it wasn't clear, I kind of color coded everything here. So your arm rotation is done by this actuator. The abduction is done here by the green actuator, and you can see that these are bolted on to each other. And then the red actuator, you can't actually see. This is kind of the yoke that comes out. The actuator is actually in the torso, kind of back in there, and it has that connected to it that allows you to then rotate this whole upper arm mechanism like that. So that's the way, one way of being able to do a shoulder. And if you go out there and you survey like all the bots out there and look at all the shoulders, right from the ones that have been around a while to like the most recent one just a few days ago, Borg One, they all have something in common, and that is they're all FAR. You know, it's like, man, didn't anyone come up with something? You might a little bit say, wait a minute, I see some subtle difference. It's like, no, they're all FAR. If you look at all of them, and any sort of nuance that you're seeing in there, we'll try to explain because otherwise the episode would end right here. All right. So, so I had to kind of dig a little bit deeper to see if there are a couple others. And I remember a few years ago, and that I did find one, which we're going to go into right now, which is from Agility. But if you actually look at all the designs that are out there, it's just like it's here. First, second, third generation are all here, and with just two exceptions. And the first exception is this one, Agility. And again, when I first saw Agility a few years ago, and I saw the shoulder, I was actually kind of excited. It's like, all right, someone is actually doing a different shoulder now. This is when they had a four-axis arm. They didn't have any wrist yet. It's like server early version that's going on there. But you may not be able to tell right from here that it is a little bit different. So here's kind of a close up. So right here, you can see these black actuators, and they are actually the first one, and that is the articulation. And then it's carrying up in here the actuator, which does the flexion, and then down here is the rotary right in there. So that's an R4, okay, an AFR design. And I was like, oh, cool. So someone is actually coming up with something a little bit different. And what's interesting about this is that the way this articulates, it kind of lifts the shoulder up. It does kind of like what our scapula does. Now, just for something everyone to understand is that even though everyone thinks their arms are 7 degrees of freedom, they're really 8. Some people might argue 9, because while there's a ball and socket joint in there, the cup that holds a ball and socket joint, we can kind of move around a little bit. Now, just explain that for a second. I will kind of briefly stop the share. So like if you ever hunch your shoulders like that, it's like what you're doing is like you're taking your clavicle and you're moving it up. You're actually taking the point where your arms are just moving up. And if you go forward or backwards, it's like you got like a lot of movement, which is what that scapula does in there, which would bring like an extra sort of dimension to what's going on. But that's just too complicated for humanoid bots right now. Clone, yeah, they'll do it. But everyone else is like, no, we're just going to go ahead and put that in there. So seeing them doing that, it means like their bot was almost doing something like that, which is why I said, oh, that's kind of exciting. Even though it's technically not like it's still, if you were to build the whole thing out, it'd still be like a 7-axis arm. It was like interesting to see that whether there would be any benefit or use to it. And so it's like, oh, okay, good for them. When the Gen 2 a digit came out, and this is what the shoulder looks like now. It's an FAR design, as usual. So they have the flexure actuator kind of built back here at the torso. They changed the design quite a bit. And and now this is a full 7-axis arm. So before they didn't have a wrist. And if you notice, when we go back up here, you see the elbow has a little offset in there, stuff like that. Now their elbows in line, they have a full wrist and everything else. And in doing that, I guess they decided that there wasn't any benefits to this. The only thing I could see is that if you look at the packaging, it doesn't, I guess, package quite as well because you see there's a lot of stuff that's kind of here. And it may be that they decided that this is a much sleeker, cleaner, more compact design. But at least they examined it. They looked into that space and they came to the conclusion that maybe this was the best way to go. Okay, so does that leave us with any other unique shoulder designs that are out there? Okay, so in order to get a unique shoulder design, we now have to switch over to agility. Oh, not Aptronic. Okay, Aptronic and the Apollo robot. So Aptronic, as some of you may know, is almost exclusively linear drives. A lot of other companies are all either exclusively rotary drives or kind of a mix. And when it comes to shoulders, even those that are using a lot of linear drives out of places, they're like, no, we're just going to use rotary here. So Apollo is the only example of a company trying to do shoulder without any rotary drives at all. Okay. And we're going to kind of break down how they are doing that right now. But pretty much it looks like the flexion goes right along this red axis here for sure. And at this point here is where the abduction happens. And it looks like the rotation also happens up there. Now, just based on that, Marla, what do you think that is? Do you think it's FAR? Or do you think it's another arrangement of letters?
I think it's something else.
Yeah, it's something else. It's going to be a little bit tricky to kind of tease it out exactly what it is. So, like right from this image, you can't tell. You need a little bit of help. And the first thing to remember is that, like I said, that Aptronic does not like rotational actuators. However, they've made an exception in two places, and that is in the hip design. The R axis is actually a rotary axis, and they have the cardan joint down here, along with the two linear actuators that have the parallel actuation strategy to get the A and the F. And even with their waist design, the Z is done also with a rotary actuator. But everywhere else, it's like, everything is linear, including their head. Their head, they don't have anything rotating up there. Everything's just kind of moving around. So it's like, I'm really impressed. It's like, man, you think that at least they do like the flexion or something like that with it. But no, they don't. And so from here, we might get a little bit of a clue what's going on. So I want you to kind of keep your eye around this point here where you pivot. And if you look at that and you see the way the arm is, it looks like the flexion might come kind of last. And it'll be pretty clear in a second how they're doing it. And it may not be obvious right now, but if we go to here, I've been able to label it. It's actually ARF. And that is, we can see right here where the rotary axis is. And you see the rotary axis is no longer vertical. That's because it's been rotated by the abduction. So that's how we know abduction comes first, and then we can see that comes second, and we can see how the flexion comes in here. Now, the way they do it is they built a cardan joint. And again, there's basically two types of joints. So there's a pin joint, which is like a cylindrical joint, and there's a spherical joint. One is 1 degree of freedom. The other is 3 degrees of freedom. There's no such thing as a 2-degree of freedom joint for rotation. Okay. The way you do it is you stack two pin joints together to give the illusion of a 2-degree freedom joint. And that's what a cardan joint is. But still, it means they have to come in some sort of order. So even though the actuation is parallel, what happens is that they rotate about this axis first. And the way they do it is you might see these linear actuators that are kind of stuffed right in here. There's actually two of them. The second one you can't see because it's immediately behind this one. And when both of those push together, you can see there's a moment arm between this point here and that point there. That causes the rotation about the green arrow. Both of them go there. Now, if they decide to go different distances, different lengths, one of them pushes and the other one pulls, that's going to cause a rotation about the blue axis. So that's how they do the parallel actuation for both the abduction and then the rotation. And now they have this rotation here for deflection. And that's actually done with a linear actuator built into the arm. And it may not be obvious. So what's sort of going on is that you can see this linear actuator right here, which I'll say it's basically in your biceps right now. So there's like a linear actuator up here in your bicep. There's another one you can't see, which is down here in your tricep. Okay. The one that's up here in your bicep pushes here to make the elbow go back and forth. The one that's down here in your tricep is connected back in the shoulder, and that's the one that actually makes it go back and forth. So that's
Like barrel actuators.
yes, yes. So one of them, this one up here is for the elbow. The one you can't see, which is immediately behind it, is the one that does the shoulder. So they found some clever way, just using linear actuators to do an entire shoulder. Okay. And because of the linear actuation strategy, of course, you'd expect the order of operations to probably not be FAR. So in many cases, these decisions in the order of operations will come down to your actuation strategy. It's and for this, if you're going to be stacking serial or rotational actuators, it makes sense to do it in FAR just because the packaging and everything works differently. But if using this kind of scheme and you think about it, this might be the ideal. So they're like the only other one that's out there for the most part. They're the only one that's not FAR right now. Because as you can see, agility gave up and they've joined that whole crowd. They're over there. This is the really only example. And I even looked at like iron from Zpeng, which is also like lots of linear actuators. And it's like when it comes to their shoulder, no, it's rotational. It's FAR just like everyone else. And then here's a good close up of like I say, the latest entry, Borg Robotics, where you can see it's a very classic FAR kind of design here, where we have the flexure there. And again, there's kind of this yoke, which is what we were sort of seeing in the Optimus design, but we couldn't see what was behind it. It comes out here to support and hold on to the abduction actuator there. And then we can see the rotational actuator is built right in there. So that's just kind of a classic design that everyone uses. And we'll be talking to Lorenzo, the CEO of Borg, in about a month or so up in Detroit when I'm there for the Automate show. And so I'll get a chance to have a live look at that. So just put that on your calendars. It's going to be an interesting conversation. Okay, now, just sort of a reminder of that, when we looked at the hip and it was a ball and socket joint, we decided that, well, let's overlay the humanoid bots to see how good a job they do of emulating that. And the one thing that we kind of notice is that everyone's sort of missing the fact that the rotational axis is not where it is in the human body. The human body, it's not along the femur. And of course, that's what ends up happening with the humanoid bots, because if you put the R axis down there, actually built into your leg, you're going to rotate about your leg and you're not going to rotate interior, which is the way you would like to. So the question is like, well, what about for the shoulder? Is there a problem with the shoulder? Is it really going to be all set? But well, if you look at this and we kind of go back here again to the human hip, you'll see there's this thing called a femoral neck, which causes an offset between the center of the femoral head and the center line of the femur itself. So you see there is already a built-in offset between the two. You go to the shoulder and it's like, it's not so much, It's we don't really have a neck there. So if you kind of look at the center line of the humerus and the center of the ball, it's not that much. If you're really going to say you want to get it right, it's like, you got to get that scapula and all that working right. People figure out how to get that part in there, and then we can start talking about what you might be getting wrong with it. But for the most part, it seems like it's not a big deal because that offset's very small. So does that mean every single FAR design is concentric? Um, And before we answer that question, I'm going to remind everyone of these two angles, dihedral and anhedral, which we talked about last time. Dihedral going up and anhedral down. You typically see when you talk about airplanes. And we brought it into this context because of when we went to the hips, there was one hip that had a very odd angle to it, which came from P&D Bonics, which I'm calling an anhedral angle in the pelvis, where we can see the red axis here, rather than being horizontal to the ground, has a very big 45-degree angle. And we talked about the consequences of doing something like that. Okay. So, what about the shoulder? Can you have like an anhedral angle there as well? Like, well, I don't think anyone would want to, but it actually makes sense to have a dihedral angle. And this is one of the first, not the very first, but one of the first that I saw doing this, as we can see here from P&D Bonics with their atoms, which is a very clear dihedral angle here in the shoulder. Um, and we can mark that out. We can sort of see how that is. And the other thing we might notice is that the rotational axis here is offset from the center. So this is no longer concentric. And the question is, why are they doing that? Okay. Now, if we look at the Atlas spot, we'll notice they've done the same thing. They also have like what is clearly a dihedral angle. I mean, they've done some other things here to trick your eye into thinking that the shoulder is swooping down. I don't think it is. I think it's just kind of that the way they built this. But if you actually look at the rotation of deflection, it's going off in that direction. And that's the thing that's important. We're going to address why that's there. But we can see there's an offset here that these are not concentric. It looks like none of them kind of intersect, which is kind of weird. This is going to make it hard on the kinematician to solve all that stuff. But I believe the reason they are doing that is that if you want your arm to be able to reach all the way down, which it needs to, in the neutral position, it needs to be straight down. The stronger the dihedral angle you have, the harder it is for this joint to rotate without coming into a hard stump. Okay. So if you actually put this thing over, it would kind of bang right there, and that would be as far as this thing could rotate. And by putting this little offset in there, it actually allows you to increase your range of motion there. So that's part of the reason of having that little kind of dog leg there coming on out here for that is it just allows you to be able to have greater range of motion in there because this dihedral, we're going to talk about why you want to do it in a second, what it's helping can also hurt you on the other side, and that is your overall range of motion. Okay, now the first spot that I saw with this is one that no one probably remembers anymore. It comes from Giant AI. They were a Silicon Valley startup that Robert Scoble went in and kind of gave a video on them about 3 years ago. I think in June of 2022, like 3 or 4 months before the Optimus reveal. So this is like one of the first ones that we had a chance of seeing. It was just a torso, an upper body, basically. It was all tendon driven. So all the actuators were like down here, and everything, including the shoulder, was done through tendons. And you can see this is MEF-AR design. There's like the rotational axis is down here. There's above the elbow. We can see the abductor right there. And we can see where the flexion is happening right here. The one thing I want you to notice is that it's not it's not horizontal to the ground. It has a little bit, maybe 7 degrees or something like that, um, of that in there. Now, the question is like, why do you want to have this? And at that time, I had done an episode with Dr. Know-It-All where we did a big breakdown and we were trying to anticipate what the Optimus spot was going to look like at that time because we had no idea. And this is kind of the first example. And I noticed that right away. It says, oh, that's really good. I'm glad they have it. And the reason is that with my own experimenting with my own avatar, which wasn't an actual humanoid bot, but it was like a virtual human, I discovered that I was having kinematic problems when I would go with the VR and I'd put my arm straight out. And that is because when you take the two axes, if you rotate the abductor 90 degrees, now your F axis and your R axis are aligned with each other. And you are in the singularity, sometimes what people will call like a gimbal lock. And you want to try to avoid that. And so what that means, if you don't want to be the singularity, you kind of have to always keep your arms down. But if everyone your arms up straight out like that, you're going to be right in the singularity. And I realized that, one way to solve that problem is just rather than mounting my arm such that it's sort of horizontal there, is kind of angle that that axis, the flexure axis, up this way, and that moves the singularity to be up higher. More where you generally won't be a problem. And the question is like, how much do you want that to be? And my feeling is like 15 degrees is about the minimum. I was getting away with 35, 45 degrees. Now the thing is, with my virtual bot, it's very easy for me to make the joints have absolutely no hard limits or stumps. I can make them go wherever they want because I'm not dealing in the real world. In the real world, when you start putting that up, as we were mentioning, then suddenly the abduction has a harder time getting back down. Because remember, we still want our arm to come down here. Not only do we want to come down here, we want it to be able to come across. So your abduction has to be able to do a little bit more than just come down straight. And the more you move it up there, the harder and harder it is mechanically for that joint to come down there without hitting a hard limit. So that's why that little dog leg and everything else coming out there is to give it kind of the breathing space so you can get down. So I could put mine up at 45 because I'm looking at it. It's like whoever really goes beyond 45 and except like maybe some gymnast or something like that. But for the most part, you're not up there. You can kind of avoid it a little bit. And so they're all playing with like, how much do we need to avoid that? And that's why they're putting in the dihedral angle. Now I had made a pretty much a big stink about that, on Dr. Noel about like, this is very important. You're going to be doing that. And I don't know if anyone listened because it's pretty clear that in the early days, absolutely no one was listening. These are the only guys who figured it out already early. But then, you know, the Optimus reveal happened and you see Bumblebee and you see zip, no dihedral angle. And then the Optimus Gen 1 came out, and I just rambling. It's like, oh, why are they doing that? They have to mount it a different way. Now, obviously, sometimes it's just neater and prettier to mount it on perpendicular. I mean, that's what the aesthetic of your eye says. You could do it that way. So then I was very happy when Gen 2 Bot came out, and they actually gave it a little bit of a dihedral. So you will see that it's in there. And so, a closer up look at that, and you can begin to see that. And they might have about 15 degrees. I think I tried measuring or something like that. It might be in the order of that 15, no more than 20 degrees, but at least I have something. So what about everyone else's dihedrals? Who has them and who's not? And as you start to go through, you begin to realize a lot of them have it. Now with Unitree, I looked at this like 3 different ways. Is remember, we thought they had an anhedral down here in the waist, and it turned out it was just the waist cover that was tricking our eye. And that's why with Boston Dynamics, I did the same thing. I was just like, oh, I just want to make sure the covers aren't tricking my eye. And I actually, kind of looked at it and say, oh, okay, that's where it's actually rotating. So Unitree, you'll see it's up here. And I'm just wondering, is that the covering that's doing that? And I really do believe that they do have a dihedral angle here, for sure. And if you look at it closely, it's a little hard to see. They may even have a slight offset. If you look at the rotational axis here, I don't think it goes exactly through the center there. So they're doing a little bit to make it easier to kind of fit in there. So they definitely have done that. This here is the iron. It was really hard to get some good pictures of their shoulders, but it is definitely an FAR design. You can see the rotation that's here. It's coming on up there. The abduction is back there. It looks like they have a certain amount of offset. So they played a lot with the offsets in the packaging of it, but basically it's an FAR as well. The original, now this is where it's going to get a bit interesting here. We'll coming back to this in just a second, but if we look at figure, this is figure 1. I'm pretty sure that was no dihedral, and they ended up putting in a dihedral here, but a little bit more. So we're talking about airplanes. Airplanes not only have a dihedral angle, but they also have a sweep back angle. And it turns out that what they've done with figure 2 is not only do they have this dihedral in here, they have sweep back. The shoulder actually points backwards. And I had a chance to talk with the chief designer about that when I saw it. And I said, you guys did this to avoid the singularity, right? He said, yep. So to avoid it, and that's also clever because a lot of times it might be that sweep back almost gets you all the help that you need because a lot of it is like straight out is what you're worried about. How often do you really put your arms back like that? So that means that's like it's a position you just wouldn't get to. That's why they were able to put the ketchup up so easy. They were able to go through. You say, oh, looks like they passed through that singularity. It's like, no, they did because the singularity is pointing back. That
By the way, do other company do this technique or
those
not?
are the only ones I've seen to do that. They're the only ones I've seen to do the sweep back. Yeah. So to me, it was like, oh, you guys really, I mean, because they understood the problem, they understood the mission, and that is we got to get rid of that. Now, this is the one that threw me for a loop. We looked at them last week, and this was Neura, and this is the only example I have like of an anhedral angle. All right, it's like, oh, what are you guys doing? Now they may have like, even a little bit of sweep forward. I'm not sure, but um, it means like the singularity is right down in kind of an area of your workspace. It may be that they're confident enough that they can kind of work around it through software and a few other things. Um, you kind of can dance around the singularity if you're really careful. Some people say it's not a hardware problem; it's a software problem. It's still it's a little bit more there. There's real physics going on that you just can't avoid, and that is that if you're moving near the singularity, you might over torque, over speed some of your motors. So, obviously, they must be comfortable with that. I mean, I must say, from aesthetically, it looks very nice. It's that's almost like the way you'd expect your, the deltoids and everything else to kind of come down and form that angle. But you can't design these things just on aesthetics. You got to remember there's some engineering that has to go in there. So I hope to get a chance to meet someone from Neura and be able to find out a little bit more of what's going on. That would be the first question I have. Like, okay, this angle, why are you so confident that you can do that when everyone else is really going dihedral at that point? So okay, now that's normally that would be it. Okay, that's all I got. Uh,
I don't think you're done.
no, 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 no. So now it's when I guess this is like almost the editorializing part of it. It's like, well, why are they doing this? Because remember, a hint is like, why are they ignoring novel shoulder designs? Why have they just said this is it? And why aren't we seeing anyone trying anything else, or are they? Now, of course, you heard me rail against the fact that I wish someone would come up with a ball and socket joint that just worked right. And just for a reminder, everyone, how a ball and socket, it's like you all have these in your house somewhere, on a tripod, and it's a very easy kind of mechanism, and that it just has to go into a cup and it can move like all around. Now, the problem with the ball and socket is that by its very nature, I mean, you think you can reach everywhere with it, but if you're going to have something out there, as you can see, there are hard limits. I can only go this far and that. So in these two rotational directions, I'm really limited. I don't even have 180 degrees going back and forth. However, about this axis, I can go like on and on forever, and that's really nice. And part of the reason is that you need to have this cup that holds it in there. And the cup has to be a little bit more than a hemisphere in order to kind of keep it in. Otherwise, it will just kind of fall out and be too sloppy and everything else. And the problem is figuring out how to actuate this beast. And I've got some thoughts about that I will share at some point. But right now, no one's really figured out how to come up with a decent ball and socket chuck. Um, and so you take definitely a different approach, and we'll probably talk again. I mean, we talk a little bit about what is the point of flexion, what is the point of the abduction from the standpoint of kinematics? Why are they important? Why do they need to be there when we start ranking axes? So, is there some other ways that could be investigated that we could look into? And
With the shoulder.
yeah, this for the shoulder, and potentially it could also be used at the hip because remember they're both kind of ball and socket joints. So if you're able to solve one, it also could do the wrist. And you could also think about it with the ankle. I mean, in a sense, all of those could be ball and socket joints, even your head. You could think about it that way. But they've all had different reasons to actuate the way they were. But if someone came up with like some kind of ball and socket joint that really worked well, that you could actuate, there would be lots of joints that you would just replace. I mean, it's like we're pretty much just your knee and your elbow are the only ones that aren't like a ball and socket. Everything else, your waist is, just going down the whole thing. So, all right, how would we think about redesigning the shoulder if we wanted to? Now, um,
So this is your design thinking here.
yeah, this is my design thinking, which some people are going to say I'm off my rocker. This absolutely crazy. But what I want to do is I want to plant a seed somewhere with someone who is maybe better at mechanical design than I am. So the first thing I want to look at is like where'd this whole sort of far um, mechanism come from? And you don't have to go very far uh, to to realize that all they're doing is stealing something out of the old, industrial robots playbook. And we're going to actually look at the wrist. You can say, wait a minute, the wrist, that's not the shoulder. It's like, yeah, it's basically the same joint. And that is, if you look at a traditional robot wrist, you're going to see that they have an axis here, which rotates like this. They have another axis, which rotates down that way. And they have a third axis that rotates this way. Okay. And this kind of wrist mechanism, sometimes they call it a spherical wrist. And the reason they call it that is because the wrist can basically point, the Z axis arrow, the blue arrow coming on here in any direction in space. You're unlimited. And it's also usually referred to as a ZYZ wrist. Now, the Z axis is always defined to kind of point out the end of the mounting plate like this in robotics. But people will also say when the Z axis is also comes up off the floor. So if you're a little bit confused, it's because when we get to the elbow, it takes a 90-degree turn and the Z axis is now considered pointing along this direction of the arm. Okay. So if you look at this, and if you look at this, what's typically the fourth axis here, I can rotate that and you see I'm rotating about the blue axis. And then I can take the black axis at the very end, which is the mounting plate, and rotate it. And this is basically what a singularity is. We are actually, this neutral position is actually the singularity. We're at the singularity there. And then you see we have this one where I rotate that and it's rotating about the green or the Y axis. So again, you can see Z, then the Y, and then Z. So that's why it's usually called a ZYZ kind of wrist. Okay. But what if we take this axis and rotate it down 90 degrees right there? Well, suddenly it starts looking familiar, doesn't it? That's the way that shoulder's working. This is our flexion, this is our abduction, and this is our roll. It's the same thing. And again, they're using kind of the same old trick because, you know, there's many ways of doing this, but you can have a motor here, or in some cases actually back there, that rotates the whole wrist, this whole end of arm here. And then built in right in here, also a servo drive, which is what allows this thing to rotate. And then finally pop one more back in here that allows your mounting plate to rotate. Exactly what we see. So again, I'm saying, hey, um, since you're stealing from the playbook of a robot and on how to design something like that, why don't you look at some of the other risks that are out there? And that is something we can do right now. So what I'm going to do is I'm going to bring up uh, first this one here. So now, and maybe before I do that, I can also wax a little bit about the history of robotics and everything else and what's been going on with the wrist. So as you see, the robots themselves can't do anything. They're designed to carry something at the end. So you put some end of arm tooling along here. And while they can package the cabling going through here pretty neatly to get what they need to make these servos move and everything like that, once you put your end of arm tooling on there, it's really hard to get everything to go through that you would like. So if you have a spot welding gun on there, you're going to need a really high amperage cables that are going to be on there. You may also need some high pressure or something like that. If you're doing arc welding, you'd have a wire feeder. If you're doing sealant, you'd be able to have a sealant dispenser and get all that stuff out there. And if you're doing painting, you have the same thing. You've got to get the paint out there. So what usually ends up happening is that you need some sort of cable management system that sits around that allows you to get all this stuff out there. And of course, the problem with all these things is that you'll see is that over time, depending on how you do it, the cables can get all wrapped up and, gets kind of nasty. And you would like to have some sort of cable management system that you don't have these things. And we've seen that with humanoid bots, we've seen all these wires are out there. How do they manage that? Everything else. So one of the big things is the solution in robotics is like, well, how can we go ahead and get rid of this awkward cable management? Is there any way we can bring it through? And that was definitely a problem with painting robots. And so here's an example of a Fanuc. I think it's a one of the P series robots that was actually designed by General Motors back in the 80s. And then General Motors and Fanuc had a partnership called GMF for a while, and basically they handed the IP over. But it's still actually built in the US. And this is a GM design. And the whole point of this thing, believe it or not, is this is a hollow wrist. So this wrist is designed that you can put all of your basically the feeders that you want for your paint gun right through this wrist. It's designed to go through there and comes out here. And if we look in closely, we can say, oh, sure enough, there's a big hole in there. Okay. So they figured out how to build a wrist, which is hollow, which is like, oh, wow, that means I can get all my cabling through there, right? That would be kind of nice. Uh, and the way it kind of works is so that, the same little way here. I got this axis here. So you get an axis here that rotates. That's kind of your fourth axis. You have this axis here, which is your fifth axis, and then your sixth axis right there. And it's done in a very interesting way to be able to put these things through, and that it could operate kind of like a shoulder. Now, the thing to notice is that these rotations are not 90 degrees apart. And sometimes this is called a triple roll wrist because sometimes the Z is referred to as the roll axis. So you get like your Z here, and basically you took a little turn and your Z goes down here, and then you turn back again and your Z goes out this way. So it's like your Z is just flowing on that way. It's almost like three Z's in a row, but you've got this little rotation that has kind of brought it down. And I think in the case of this, it's almost like 70 degrees. Now, the thing with this wrist is it's not considered a spherical wrist because it's actually impossible to go all the way back. You cannot get the Z axis to point straight back. There's absolutely no way. So you're kind of limited in the area that you can cover. However, the thing about this wrist is that if I take this fifth axis, I can rotate it as long as I want, and it does not self-intersect. I can go around and around and around. And in fact, I've seen programs where they do that, where they can go plus or minus 720 or more. It's kind of crazy that the fact that they don't have any limits. Whereas if you go down to what is really considered a spherical wrist, maybe we can look at this one right here and say, hey, I can take that and I can point it all the way back. The problem with that is this thing bangs into it. Okay. So there's always like and yeah, you can design around it that there would be like adequate space that potentially could go through. But for the most part, by the time you get end of arm tooling on there, it's going to self intersect. These things are limited to about plus or minus 135. So even though in theory, I can make the blue axis point all the way back, so I can point to any place in the sphere, the reality is I'm limited. And I'm limited to a hard stop. So I go bang right into it, which means I have to slow down and make sure that when I get to that limit, I slow down. The beauty of this, which is something I always love, is like, okay, they're saying, there's part of this of the work envelope around the wrist that we don't want to go to. So don't design a wrist that actually allows us to access it. So the beauty of this is like, well, you can't access it. You don't want to access it anyways. And we just design it so it just, you theoretically can't get there. Yeah, I mean, you could put a hard stop, you could mechanically do it, but that's the difference between like the theoretical design and then your real world design. And this is kind of great. Is like it's kind of wow, it works because theoretically it's sort of designed to do that. Now, the one thing that this might be kind of odd to me, like, well, how could you build a shoulder joint out of this? I mean, that would be a bit weird trying to figure out how to get it around the way that you want. And kind of agree, it seems a little bit strange, but this angle that's there, that's an artificial angle. That can be any angle you want. They put it in there because that's ideal for what they want for paint. The bigger you make that angle, the more you can wrap around and point backwards. But if it's not that important to point backwards, you could change the amount that you have there to give you the motion that you want. And again, go back to that ball and socket joint that I just showed you. There's limits. Theoretically, the ball and socket joint is a spherical joint, right? You can go anywhere in space with it. The reality is you can't because you need that cup that's kind of holding it in and your ligaments and everything else. So you're already constrained in the amount of movement that you have. So you might think about, well, wait a minute, with that in mind, let's think about what our mechanism is going to look like. But there is this kind of weird offset that you'll notice it kind of goes around this way. And that's all intentional because they kind of didn't want the plumbing to tie itself up into knots going through here. So they intentionally wanted to have these graceful uh, raises or curvature kind of going through for it. because otherwise, if you had wind up and you were rotating the sixth axis and the rest, the hoses and everything might just get kind of tied up a bit funny. Now, that's one possibility. The other thing that I would look at is this one here from ABB. Okay. Now, this is originally developed by ABB Tralfa. Let me get this one kind of out of the way for us, right? Well, I'll just move it on up there so it's not in our way. Um, that's the Norwegian division of ABB, and actually it was an independent company in Tralfa that built the world's first paint robot. And they built it because they were building wheelbarrows, and their wheelbarrows needed to be painted, and they wanted to try to figure out a way to paint them automatically. And that was done like in 1967. They came up with the first um, robot for painting, and then eventually they got bought by ABB. And then the clever engineers down there figured out how to come up with another kind of hollow wrist. Now, this hollow wrist is kind of interesting as well. And the reason why it's interesting is that even though it's kind of a three-axis wrist, it's got two kind of coupled axes here. So I want you to see that, your traditional fourth axis here that's able to rotate around like that. You have this other sixth axis out here, which, so again, it kind of looks the same. But then you have this thing here where these two pieces kind of counter rotate with each other. Yeah. And again, it's still the same issue that it can only point back so far. And I think that the angle that's in here is 55 degrees. That could be a different angle. And because it's 55, it's able to effectively point back 120 degrees. So around the whole thing, so that gives you pretty much, it doesn't go back 180, goes back. Maybe that's enough. You could play with that. But again, this looks like, an interesting kind of mechanism that, someone could figure out the inspiration. Now, how this works mechanically is a mystery. It's really easy to create these things in computer graphics to show you what the exterior looks like and how it works.
Is it even possible to
Oh,
do
yeah,
that?
yeah, yeah. I
It
mean,
feels to
it's built. I
me
mean, they make these things. I believe the servos are all back here. There's no servo in here, which is a plus, right? Because the whole thing that Bear keeps on talking about is you want to put all your mass towards the torso as much as possible. Wouldn't it be great if you could put all your servos in the torso and just not have them? So, this is a kind of mechanism, the way it's designed. Obviously, it's got some interior gearing and some other things that allow it to do it. But the actual servos for really, they're not in there because this whole thing is hollow. I mean, it's like really hollow to be able to get everything through there. So it means these kinds of designs already exist. And I would love it if someone would take some sort of inspiration and imagine, could I build a shoulder joint about that? Now, the one thing about this and this versus this, what's one of the differences you can see about these?
the axis orientations
Not
is
so much the axis orientation. And if we go to the actual robot arms themselves, that they all have something like this. This is your classic pinch point. Things get stuck in there. These things are sealed. There's no pinch point. So it's like, wow, that's like another huge advantage to this thing. there, there's just absolutely, your cabling goes through. You don't have any pinch points. Your range of motion is exactly what you need. It's not more. You don't have motors that in theory can go infinitely, but you're never allowed to use it because other things. No, these things can go quite a ways. Um, and the other thing about painting robots is they have to be something called X-proofed, which is explosion proof. Paints have solvent. And one of the problems of having these all electric robots in the paint booth is there is concerns like, well, what is you get a spark? So they have to make sure that the solvent can never make its way into the servos in any way whatsoever. The control cabinets are usually outside and stuff like that because they're always sort of afraid of that. So that's like one of the concerns is to make sure. So these things are sealed up very well. So they're a very interesting kind of wrist design. Um, and it's kind of worth saying, hey, let's move on from this. Maybe there is something else we could do. Now, everybody's going to probably say, you're probably crazy. That's not going to work right. And they could be right. But I'm just hoping there's one person that kind of looks at that, scratches their head for a little bit and says, all right, might be onto something here. Maybe this is another way of being able to do a shoulder. And the shoulder may be a good place to operate from because you don't try to walk on your hands. Your hip joint is just so important to walking. It can be very complicated. Also, the payload requirements of your leg is a bit more. So it might be easier to make a joint like this, which doesn't have to worry about quite so much the payload. So that's why I'm saying that's a good place to start. But if you're able to solve that there, it may be that, wow, and then you can start looking at some other joints also out there. So yeah, that's like my little bonus for anyone who makes it this far into the video of some potential ideas.
Quick question: when you see the bench point based on the shoulder use, so do you see any bench point? Because I see in figure the way they make the shoulder, there are bench point there or not?
Yeah, there always is, in every one of them. So if we go back and I'll me stop that right now, and if we kind of go back to the PowerPoint, I think we will see they all have pinch points here, which they're trying to cover up. So they're all trying to use some kind of material or something like that to be able to get around the pinch points that you're going to have. So, oh yeah, look right in there, Unitree, and it's like I don't have my finger in there. That's going to be that has a pinch point. There still is one here. Tesla's done a much better job of trying to cover that up, but there's still some potential places that you can get pinch points. If we look at, I think yeah, yeah. So there's just going to be a place for being able to always getting someone's finger stuck in there. I mean, it's just right. They're doing their best to get them out, but there's still a potential place that you're going to get pinched in a few of them. And I think if we look at, if you look, here, there was a potential place in there, and there, I don't want to get my finger in that place there. They're doing they're trying to protect it as much as possible, but it's there. It's a lot harder to
I
cover it up.
I work in I told you I worked in the spot robot and before, and I got my finger pinched and was about to lose my finger.
Oh yeah,
It just took.
yeah, yeah, yeah. That's one of the concern, and you got many, your elbow also. I mean, that's even though they try to cover it up, the fact is the elbow can come all the way back and get your hand in there and you can get caught. And so a lot of the cobots are out there that had to do tests to make sure, they do things like, put a can of Coke in there and you'll be able to come back and like crush it and like, oh, well, okay, but again, I can get you in a headlock, that's the way the human body's designed. But, there's no pinch points up here in my shoulder. And, but for a humanoid bot, there's the potential of something getting caught there. So that's always a concern, but they're all going to have the covers on them. So in many cases, like with Neo, again, 1X, that they never make it here on my list because I have no idea what kind of shoulder they have. So it's not because I'm ignoring them. It's just like, I don't have x-ray vision. It's so, I can guess. I'm thinking it might be far also, but because it's all covered up, we can't see it. Just like we couldn't see the hip. I was like trying to figure out, is it a far hip as well? It could be, but it could also be something else. So I don't want to put something out there where it turns out it's like, you were completely wrong. You didn't know. It's like, yeah, well, did you take the covering off?
Did you see the TEDx talk?
I was like working on this all week.
Yeah, he was asking to do some manipulation in the stage. So
Yeah. I mean, and that's live demos are
yeah,
like the top.
I mean, he is confident. I feel like he was super confident.
Super common, and the thing is you need to make sure you rehearse exactly the venue you're in. And I don't think it was WC Fields, but probably was just something like never work with small children or animals, as an actor, because they'll just do something else, and you could probably add robots to that list. So you go out there expecting them to do something, and then they'll just like fall down or something. And of course, the thing is you can over rehearse. You don't think you do, and then you realize like the battery level is dead or something like that. It's like you got to make sure on all those things that whatever you've done, you haven't worn out. And evidently that's what ended up happening for the Cybertruck demo that went south when the glass broke. It's because they had tested it so many times that day and it hadn't happened, but it turned out, I think by banging the door with a hammer, it had done something to compromise the glass So when it came time to throw the glass, so it's like if they hadn't practiced, they would have been fine. But as you know with anything, it's like you hit something enough times, eventually it's going to break. So if that's part of your demo, it's like don't hit it 3 times before your demo. Just assume it's the it's the one that came off the line unbroken and it's going to
Well,
work.
I just want to say it was interesting episode, and as always, what is the next part?
Yeah, so I'm thinking now it's like I want to go back to kind of ranking joints, but also now that we've talked kind of about ball and socket joints, I might sort of talk about what my idea of how deep
Because you
storytelling.
said you want some VR with the humanoid. I think the episode we did
Yes, we did
before,
that.
when you do the for reality, you want to do that with the humanoid.
Yeah, yeah. At some point, I have a long ways to go. It turns out there's an open source model through Google DeepMind. They put something out in like GitHub of Apollo, and I've got that, and I'm starting to work on that. If you give me a minute, I can show you kind of like where I am with it and how I still have a long, long ways to go. So yeah, just give me yeah, you give me a second there, and I'll try to pull that up. Oh, I got to find my mouse and make sure it kind of comes back. But yeah, it's a lot easier if you have you know if I had something like if I had the CAD data for figure, I would have been done. It's,
Do you have it?
no, no. So a lot of them are they don't like publishing. Eventually, they all will. But right now, I can understand that none of them really want to publish it. And so I was able to get these STL files. So they're really in rough shape. And then there was a companion file with it. And I think what I need to do is go ahead and share again. And we'll go ahead and find that here. So the window, there we go. Okay, so here we have Apollo, and um, I think I've got some of the joints working here that I can kind of I have to double check. Let's see. Oh, it's interact. So I can move the joints kind of back and forth in some cases, but I'm not actually in all cases doing them the way I want. So we can see, and I've yet to get that the hands and everything else in there. Let me get it so it shows up a little bit better here. What I have done is I've managed to show how the elbow works. So if I take the elbow joint right now and rotate it, you can see that actuator. See that? So that's the bicep actuator, and that's what we were talking about. That's what makes the elbow go. Now, and I zoom this thing around here. They have a similar actuator, but unfortunately, the CAD data was kind of missing on what that's connected to for the shoulder joint. And you can't quite see it here, but there would be a linkage that kind of connects this off onto there. They say it was missing. And because it was STL data, it was like really rough in some places. Like when you look at some of the
Like you made a lot of progress. So last time I saw it was just very
yeah,
rough.
I mean, it looks pretty nice, but again, they went through it, and I'm sure they wanted to make it like a low resolution export. So it's a low resolution export with a few things that are missing, but you can see how the bicep down here is causing that to extend, and it rotates about a linkage mechanism there that's kind of bolted into here, and as a result of that, gives it the force that it needs to be able to kind of move in the flexion. Now, I haven't got to doing the whole arm up here yet. Okay, so you see this you see these holes are rough. It's like if you had a high resolution export, these holes wouldn't look so weird. The we can kind of see where this mechanism is, and again, there's like some missing stuff, and I have to go in, break the CAD down, add degrees of freedom. There is going to be a piston that kind of comes out that connects on to this part here. And then way back in here is a Heim joint, a little spherical joint back in there that's going to allow that thing to wobble back and forth. Because you got to remember, in this case, in the planar case that we're looking at here, and maybe it's better looking at the elbow, what's going on, is that as the elbow moves, you'll see how this moves way back up here. So you see there's a a pin joint right in there, which is required to allow that to move. And at the same time, when you're doing this, you see because it goes up and down, you need to have some sort of cover to kind of protect this, um, and in your whatever that range of motion is. So it pulls in like that, and then you get the elbow and everything that's moving around. So that's why you have these joints here, is you actually have to move. When you do this double thing here, this Mimo, the pins at the end can't be a pin anymore. They have to be a spherical joint because it moves in two planes. It's not moving in a single plane anymore. So that makes it a bit more complicated. It's also going to be fun down here. This wrist is like a very familiar wrist. Right now, I haven't been able to break the joints out yet. And again, it's missing some CAD here, which I'm going to have to fill in with my own. And then this is the joint, which is going to be pretty interesting. I think the way they do it is they have a rotational axis here and it's pinned on there. And that's how they're able to get kind of the spherical movement, in a clever way, that instead of a Heim joint, they're using something else there to take care of that. But that's about where I am. And then the leg, what I'm probably going to try to do is the leg. We'll see, it's the same problem here, the leg. Let me get everything back in its home position right now. So the way the leg works is, we have back here two actuators, and the actuators are connected up here in this particular joint. So when this moves forward, these actuators are kind of pushing off of here, but that's going to come out. So that's something I'm hoping to be able to get modeled. And again, by being differential, you can get it to go up and down. And let me see, where's the other joint? And then you get this. So you get it to rotate about that joint there that you can see. Otherwise, you're kind of rotating this way. Otherwise, together, it rotates about this joint there. So you can see exactly what that cardan joint looks like there. That axis here. And then we can see this axis here. And these are all accomplished by these actuators that have to get connected to here, as well as the other side. And I've got a lot of math to solve to get that to work. The constraint equations are going to be kind of fun. Um,
I wish I can play with this.
yes. Yeah. Once you get that, it's going to be fun. Now, I did get, I think, the knee mechanism to work. So we can sort of see the same thing here. So as you can see, when the knee comes out, it's very much like up in the elbow. You can see the knee mechanism there. And I think I did one thing here, which is, let's see, I thought I had a property on there. I thought I had made that possibility to make that visible or invisible. What happened on that one? Let's see. That joint. Oh, the covers. I had something to be able to remove the covers, and now I forgot where it went. It should be there. So you could see that. Actually, this give me a second, and it's like one thing between thinking I remembered to do something and having it actually happen. Let's see. If that's in that leg there, and that should be these guys here, that geometry there. Oh, okay. So let's go ahead and make that invisible. And then I think we probably want to see all that. Okay. Or maybe not. Let me make that invisible. Okay. So what we can see right now is kind of how that mechanism goes back and forth. So that's how the knee mechanism works. Again, you see it has to rotate up there. That's a pretty big actuator that they have. Yeah. So more than likely, this part up here is the rotary part. This is probably like the real servo, and this here is like the transmission system, because we need a lot of travel on that. So you see how much of that pokes out? That's a lot. So all that has to be able to retract back in there. And not only that, so when it retracts back in there, you got to remember when it sticks out, you don't want just like a little bit left in here. You still need to have a certain amount in there to be able to handle and carry the load. And these things are working through a transmission system, which is a roller screw, which is basically that's threaded. And as you turn the nut, it causes the threaded part to translate up and down. So in order to get that long range of motion, that's probably what this big part here, that's your transmission. And up here, this is pretty much the part that does all the spinning. So you're taking rotational motion you're turning it into linear motion to create rotational motion. Because then in the end, that's what you're doing is you're rotating about that axis right there. And then I think it makes it right to about there. Yeah. And of course, the problem with a mechanism like this is your range of motion is really limited to less than 180 degrees. Because you see, if I try to go much beyond this, if this thing passes through that pivot point, I get into a deadlock where I get opposite motion, depending upon what I want. And a lot of us may have seen mechanisms which are kind of like that. And there's sometimes some weird pedal mechanisms that work that way. That a lot of times it's just the inertia that allows you to get through. But without that, you can get in a deadlock situation that if you're past it and you pull on it, or it's just going to go in the wrong direction. So you're limited there. The other thing is at this point, this is the force is along that rod, and the pivot point is right there. So if you start drawing your vectors, a vector from here, let me zoom in a little bit more so everyone can see that better. As if you draw your vector here, which would be your radius, we get right to a nice view here, more clear. My radial vector is this way, and my force vector is this way. And of course, I would prefer that my force be perpendicular to my radius. So what that means is effectively my moment arm is like just the distance from here to here. It's not that distance. So it gets shorter and shorter. And you don't want to go much further than that, because you go much further than that, then you're going to be pulling right through the center of rotation, which means you have zero torque. So as you're moving it, the amount of torque you're getting on that knee is getting less and less and less. In some ways, it may not be bad because you need this thing to slow down because you're getting towards the end of motion and your range of motion. But then when you get up right about here, you see this is where you now have your maximum. You get a lot of torque there because your moment arm gets very, very big. And then as you kind of continue on, it's actually shortens again until you get to this point that it doesn't make any sense. And again, you have to be careful if you have this thing extend back too far. When you push on that, rather than rotating in this direction, it could continue to rotate all the way around because you get that deadlock. So right there, man, that is really small. So they have to give like a lot of force just to get it to kind of unlock and bring yourself around. So that's one of I guess you say the problems with using a 3-bar mechanism like that is that at both extremes, your torque basically goes to zero. That's why you can't go 180 degrees. You have to like maybe 150 or something like that. 135 is probably best that you have a reasonable range of torque all the way through it. Otherwise, you don't. And this is why some have gone to the Hurricanes design, which is a 4-bar mechanism, which allows you to keep the torque more consistent over a wider range. And that's what Tesla and Xpeng did in their iron bot. They add a little bit more. I think also that the Romella on me was designed that way so that if you're using that, you need it in order to be able to get that. But in this case, Apollo decided, or Electronic decided that 3-bar mechanism was fine. That rather than going into like more not just expensive, or, kind of complicated mechanism like the Hurricanes, that it was just best to do 3-bar. And so that same problem is happening at your wrist, or sorry, your elbow as well. You're going to have it that you can only, your torque is going to vary over the distance when it goes back and forth. So this is why, no one else is attempting to do this. They are like, all your joints are rotary. Your joints are just rotary. And if they're rotary, why do I want to convert rotational energy? Because all motors spin. There's some rare designs of like linear induction motors and stuff like that. But for the most part, all motors, they just spin. That's how they work. And so you get rotational energy, and you want to figure out how to take rotational energy and convert it into linear energy. And there's lots of ways you do it with tracks and stuff like that by having a racked and pinion and other things that kind of do it. But if the idea is that you actually, rather than having thing coming in motor spinning, you want to have the thing in motor kind of extending and coming on out, then there's a little bit of that trick, which is the roller screw, which goes ahead and does that and gives that to you. But now you're saying, oh, all right, I'm going to take this mechanism, I'm going to connect it through a lever arm because in the end, what I wanted to do is make this thing rotate. So it's like, wait, rotation, and then not only that, it's like you've got to add these extra joints. So there's these other additional joints you got to kind of put in there. Makes it more complex. So if you're going to go that route, you better have a compelling reason to do that. And Aptronic internally believes they have a compelling reason that it is better, that that complexity actually will have its benefits over, which is why they're doing that. Part of it is that energy conversion. They believe they have much better energy conversion. Um, Also, some of they do like some of the torque capabilities that they have. The torque transparency is that it's actually cheaper, which I found to produce the linear actuators. So I mean they've been studying it for a while, and it's not like they feel compelled they have to do it, but they have a pretty strong thesis on what's doing that. So a lot of others will be like, oh, I'm not so sure that I don't want to do it. It's a lot easier to do rotary since your joints are just that. One potential reason to do that is I'm thinking of loads on your joints because a lot of times when you build a hinge mechanism of any sort, you need to build it to handle loading conditions in all directions. And if we think about it, our knee is like we do like our knees to go kind of back and forth like this. But every now and then we take a shock to the left or the right, like, think of a football player or something like that, or where you cut really hard one way. And, suddenly your knee pops, right? Because it took a force or a shock in a direction it wasn't designed to take. And so if you're turning a motor into a hinge, it has to be able to handle the same loads that a hinge would take. And if you back it off, if it's no longer the hinge, if you take it, say, I'm going to make it remote and then go through something else, that means you've now kind of isolated it from the injury that might happen at the knee. Because now I can have this hinge there that's just like, oh, rock solid. Go ahead, try twisting me. Nothing's going to happen. But, an actuator, how much can it take? And remember, actuators are very sensitive to the tolerances you have in the rotors. You want them to spin. Well, distances you have between the magnets, the closer, the better. But if this thing is getting loading, and loading always tells me, oh, deflection. You know, there's no such thing as a loading condition without deflection. It just that's what happens. And so that could be right, one of those strong, compelling reasons of why you say, we don't want that. We don't want it. Now I had others said, "Oh, we can design it." It's like, okay, all right. So you can design your motors to be able to handle that, and that's what we're going to see. This is how well they're able to kind of take all those sideway loads. They can handle torque against torque, no problem. You know, but there's torques that are going to come from other directions that will be interesting to see if they can handle it.
Well, it was great as always, and I just want to say that I didn't see anyone doing the same in-depth study as you do in HM. So, and this is something I want to mention that I'm not sure. Should we have like a series, upcoming series beyond the homoid
The wrist we could probably talk about quite a bit. The ankle. I think there's a little bit to kind of look at that. Well, we'll probably have to like the knee and the elbow. Maybe we have to do them together, but they're not going to be as in depth because I'm just not sure there's much there to cover. But I could be wrong. It's one of those things that you get into it and you realize, oh my goodness, there's some interesting stuff here or things that you have to think about. But again, the whole idea of this series is food for thought for anyone that is thinking of building a humanoid bot. If I'm so lucky that the people who are building it, if they're listening to the series and they're getting anything out of it, well, that's a bonus. So, I don't know if like the dihedral angle was as a result of my complaining about it for a long time, but it's good to see that eventually everyone's sort of gone that way because it makes sense to avoid that singularity. Um, but yeah, so again, we need a new crop of good humanoid inventors out there and start thinking about that shoulder design. And yeah, okay, my idea is crazy. Then you come up with one that's crazier. All right, let's see you do it.
Awesome. Again, I think people benefit from that. That's for sure. And I hope we continue, yeah, doing it like that and more analysis. Thank you so much.
You're welcome.